There we go. So hello, everyone. Thanks for attending this lightning talk. I'm Sonika, Johri, and I lead the quantum applications team at IonQ. And the other speaker from IonQ will be Matt Keesan. Matt, do you want to introduce yourself?
Hey, I'm Matt. I run the software stack at IonQ from the cloud down to the operating system that powers our quantum computers.
Cool, thanks, Matt. So I'm going to start with telling you about some of the fun quantum applications that we've been running at IonQ. So I'm just going to walk you through some different examples, and then happy to take questions afterwards. So the first work I want to talk about is this work on generative learning of joint probability distributions. And for more details, you can find the archive paper at that link. So what is generative learning? So generative learning is basically when you're given some kind of data set and you want to learn the probability distribution over that data set, right? So you want to create a model that can generate new samples from that data set, given the existing samples. So as we know that, quantum states are, when measured in some particular basis, they are essentially probability distributions, right? And so it's very natural to ask whether you can use quantum computers for generative learning, right? And so that's exactly what we did in this project. So here we have the data set that we used in this case was the joint distribution of the stock prices of Microsoft and Apple. And let's say you have the returns of those two stocks over 8 years, and you can visualize them as a scatter plot that looks like this. And then essentially what we did was we came up with a variational quantum, a quantum variational ansatz circuit, right? Which is related to something called a cocula, right? Which is used in finance to model joint probability distributions. And we trained that variational circuit to produce samples from this joint distribution. And we actually trained it on up to 8 qubits. So here I'm showing results from 6 qubits, comparing the classical models and the quantum models. And you can see that the quantum models actually outperform the classical models. And additionally, another thing that we noticed was that the quantum model, so this quantum generative adversarial network and the quantum circuit born machine, it actually trained much faster than the classical model. So, almost 20 to 1,000 times faster. And then additionally, what we found was that the quantum models are way better at producing samples from the tails of the distribution than the classical models, right? And these tails can actually be very important because they essentially model black swan events like the pandemic, right? So overall, our conclusion was that if you want to do generative learning of multivariate distributions, one should seriously consider doing that on quantum computers. Okay, switching to a very different project. This was around Monte Carlo simulations. This has an application in Monte Carlo simulations. And this was a demonstration of a fundamental quantum algorithmic primitive called amplitude estimation, right? And in this project, this was run on the latest generation IonQ QPU. And we showed that using this particular quantum algorithm, we could get up to 70% reduction in the error rate compared to classical sampling. And the demonstration of this quantum algorithmic primitive really paves the way for doing quantum-enabled Monte Carlo applications such as risk analysis and price simulation. And again, you can find this work in this archive link over here. Then another cool project that we did last year was this work on the generation of high resolution handwritten digits with an ion trap quantum computer, right? So in this project, the goal was to generate generate handwritten digits that resemble images from what is known as the MNIST data set. MNIST data set, which contains, again, handwritten digits. And we set up a hybrid quantum classical learning architecture over here. So the classical portion of it consisted of a GAN that functions, again, a generative adversarial network that functions as usual. And the quantum portion of it consisted of a variational quantum circuit that has parameters that can be trained. And the output of this variational quantum circuit, right, it's measured in some basis, basically, which you can again train. And the output of this is used as a prior, right, for the classical generator. And what we showed was that using this hybrid quantum classical architecture, you can actually outperform purely classical models at generating images of handwritten digits. And so over here, on the x-axis is the number of epochs in the training, right? Y-axis is the inception score, which gives you a sense of how good the images of the digits you're generating are, and how diverse they are. So you don't want to generate many. You don't want to just learn to generate one kind of digit, but all of the different ones between 0 and 9. And so these are results for 8 for the algorithm running on 8 qubits. And you can see that the results from the IonQ experiment actually outperform the purely classical model. And on the right, you have images of digits that were actually produced by this hybrid model. Okay, another interesting aspect of machine learning is, so far I was talking about generative machine learning. Let's turn to some discriminative machine learning, right? So over here, I'm showing an example of running a very simple discriminative machine learning algorithm called a quantum nearest centroid classifier on IonQ systems, right? So in this project, what we did was, so let's say you have data sets of images, right? So it could be, again, these handwritten digits, 0 to 9, or it could be like images of flowers, right? Or some data set that contains characteristics of different kinds of species of flowers, for instance. And the algorithm is extremely simple. So let's say you're given a data set with certain number of classes, right? So over here, it's 3 classes, right? And the first thing you want to do is in this algorithm is find the centroids of each of these classes, right? And then when you're given a new point, right, such as this one in the white, and you want to classify it, you just calculate the distance of this to each of the 3 different classes, and you assign the class that corresponds to the shortest distance, right? And here, basically, the way that you do this algorithm on the quantum computer is that instead of computing the distance to the centroids on the classical computer, you just compute them quantumly, right? And we did this for several different data sets. And here I'm showing you results for, again, the MNIST data set. And so we tested it on different subsets of the MNIST data set. So, just trying to classify 2 digits, 0 or 1 or 2 or 7, or classifying all the way up to classifying all 10 different classes, right? And these are results that were run on 8 qubits, right? And NC is the number of classes here, and NS is the number of shots you take from the quantum computer. So the black diamonds here are the results from classical training, and then the blue and the red bars are telling you the results from the quantum computer before and after a post-processing technique that we invented. And on the y-axis is the classification error. And you can see that in every single case, including for 10 samples, the results from the quantum computer are matching the results from the classical computer, right? And so when we have even more qubits and higher fidelity, we can start going towards cases where the quantum computer can actually outperform the classical computer. And one of the interesting things we noticed was that this is actually a noise resilient algorithm in the sense that the noise does not kill quantum advantage. So over here you have the three different classes represented by the colors of the circles, and the insides of the circles are representing the colors that are assigned by the quantum computer. And you can see that before the error mitigation, while the points in the, that are far away from the other classes are well classified, the points at the boundary are misclassified. But after we apply the error mitigation, we can actually correctly classify the points that are even close to the boundary. So in that sense, you can, it is resilient to noise, especially after you apply your error mitigation techniques. We're also doing a lot of interesting projects in quantum chemistry, right? So we had this recent paper on determining the energy, the ground state energy for a ring of 10 hydrogen atoms, right? Again, in this archive paper. And prior to that, we also did some work on looking at the eigenvalues of the ground state in the water molecule. We are also doing some other projects on looking at hydride molecules and comparing the energies we get from the variational quantum eigensolver to other benchmarks that have been demonstrated in the community. And then something that I've been really excited about over in the last few months is this benchmarking of quantum computers, right? And so I think really at this point in the quantum computing community, we are at the point when we can start to evaluate how good quantum computers are at some particular algorithm or application. So, how do you compare all these very different qubit technologies like superconducting qubits and trapped ion qubits and so on, and how useful they are for a particular application, right? And for that purpose, device level benchmarks start becoming less and less useful when you're going to more and more qubits. And if you look at the HPC community, so the supercomputing community in classical computers, they actually widely use algorithm level benchmarks, and these algorithms are supposed to be representative of the applications that those supercomputers are used for, right? And so recently there was this effort from an industry consortium to create algorithm level benchmarks for quantum computers, and I feel, and I very strongly believe that these algorithm level benchmarks, they're useful to compare different technologies as well as see how a particular technology is progressing over time, right? So, so these are some of the results, right? So over here you can see, these are some of the results presented in the paper. So over here you can see the color is representing the average fidelity as defined for those algorithms. And there are a bunch of different algorithms that were tested, right? The x-axis here is the circuit depth, which is a proxy for the number of gates. And then the y-axis is the circuit width, which is a proxy for the number of qubits, right? And for IonQ, we were able to test for up to 21 qubits, to publish results for up to 21 qubits, right? And you can see that the fidelities for IonQ were also high as compared to the other platforms. So if you want to go and test these benchmarks for yourself, the repository is on GitHub, and if you go to this paper or archive, you can find a link to the repository as well, and go and basically try running these benchmarks for yourself. What also really excites me is when you compare how particular technology is progressing over time. So if you look at IonQ, right? The current quantum computers went online about 2 years ago, right? And now we have our latest system. And you can see in just 2 years how much things have improved, right? So you went from a system of about 11 qubits to a system of 21 or more qubits, right? And the fidelities have increased significantly as well. And so this, if we can keep up this kind of rhythm, that every 2 years every 1 to 2 years, we are significantly improving the number of qubits and fidelity, then that is extremely promising for quantum computing. Okay, I think I'll end here, Matt, and I'll hand it over to you.
Thanks, Sonika. Super cool work. I just wanted to talk briefly about internships, etc. I hope everyone had an amazing hack. I'm really excited to see all the projects over the next couple hours of judging. And before everyone can rest, I will tell you about internships. So it's important to note, and this is probably true for all the sponsors, we have paid internships available in pretty much every engineering field. If you're electrical engineering, you're interested in experimental physics, theoretical physics, mechanical engineering, computational physics, software engineering, and of course, what Sonika has been talking about, applications and algorithms research. We have internships available. They are paid internships. You can email internships@IonQ.com. For the most part, if you're doing hard engineering, we'll want you in the DC area, at least through this summer. In applications land, we're able to kind of support you wherever you may be. And just to give you an idea, internship projects for us tend to be very hands-on and actually in the system. So we have interns who have publications in algorithms research. Our quantum computer environmental control has software written by former interns. Same with optomechanical assemblies in the physical quantum computer designed and assembled by interns. So really have an opportunity to make a meaningful contribution to the field. In addition to summer internships, we do have semester-long co-ops available. So if you're in a program where that's possible, or you just need a break from Zoom school and would like to come work on Prem, love to talk to you about it. You don't have to take my word for it. We've gotten really good feedback. Part of this is because we're a very small company, so we pair up interns with senior mentors to really walk you through your problems. So you'll neither be abandoned, you'll also be challenged in your work. And the last thing I'll mention, not just for interns, of course, some of you are graduating or are postdocs or in grad school right now. We have some on the order of 100 jobs open right now at ionq.com/jobs. And if you're not sure where you might be the best fit, or it's just daunting to look through all the options there, just send an email and your resume to me, just matt@ionq.com, and happy to see where might be the best fit. And with that, Sonika and I are both happy to answer any questions you may have.
Fantastic. Thank you so much, guys. Really great to hear about the work going on. So if anyone has any questions, please feel free to write it in the chat, or you can also raise your hand and I will call on you accordingly. Let's see. Okay, we had one question. Could you explain a little bit more about the applications in quantum chemistry?
Yeah, sure. Yeah, so I think the question on applications of quantum in chemistry, right? Yeah, so basically, modern chemistry is all quantum mechanics, right? So it's basically studying how systems of correlated, basically studying the eigenvalues and eigenfunctions of systems of correlated electrons, right? And their dynamics, right? And there are very straightforward mappings of, electrons to qubits. So for instance, something called the Jordan-Wigner transform can translate fermion, like an electron, to a spin-half system, which is representing a qubit. So once you do that mapping, you can study all of quantum chemistry on quantum computers, and then basically, figure out the states of molecules, and even design molecules, and study the mechanisms of chemical reactions and so on. And the advantage of using quantum computers here is basically, if you try to study quantum chemistry on classical computers, right, as you increase the number of electrons or orbitals, the size of the problem you have to study on classical computers, it scales exponentially with the size of the problem, which is represented by the number of electrons there, right? But on quantum computers, that problem, the time to solve that problem is going to scale only polynomially. So quantum chemistry is one area where we expect exponential speedups for studying problems on quantum computers versus classical computers.
Thanks. Looks like we also had a question about internships. I guess for Matt, if you could repeat. So the process for people who are interested in internships, I see they have the link there that they can go to. There was a question if you guys accept high schoolers, or is it undergrads and above who are preferred?
That's a great question. I put in the chat the email to send an internship inquiry to send your resume and some info about yourself and what you're interested in to internships@IonQ.com. As for high school, we have taken high school interns in the past. And in fact, we had at least one in applications last summer. Is that right, Sonika?
Yes, we did.
And then which went great. And so it's important to note, depending on where you're located, there could be limitations. So most of our interns we've taken from high school in the past have been local to the DC area or in Maryland for obvious reasons. And part of this is because in the US at least, labor laws really vary by state about like what you're able to do and so forth. But if you're interested, don't let that hold you back. Just send us an email and we'll figure out what's possible with you.
Fantastic, thank you. Any other questions? A question if you accept interns from Europe.
That's a great question. It has been possible in the past. I think we are not a large company with offices all over. And so typically we preferred interns who can physically be with us. Obviously with the pandemic, it's a bit dicier. So I don't want to get anyone's hopes up, but if you're in Europe and interested in a potential internship, please email us and we'll talk to our people operations folks and see what's possible.
Great. Yeah. For anyone else who has questions about internships, sounds like the best way is to email Matt's email right there. And also, of course, we have some IonQ representatives on Slack as well. Are there any other questions? Great. If not, thank you again so much to Sonika and Matt. And thank you indeed to all of our presenters today. As a reminder, we will now move on to the judging portion of our event. So all the participants who submitted a project via the GitHub, you should see in the Slack a link to the spreadsheet that has instructions about which judging room you're in and where to go. Please feel free to message us on Slack if you have any issues with that. Otherwise, the next portion that will be streamed to Twitch and you will be, in general, the next presentation will happen at the end of that. So please join us later for Lightning Talks. And in the meantime, enjoy those presentations. Really looking forward to hearing what you guys have produced this weekend. Thanks so much.
Thank you.